Welcome to the second part of the first lecture. In this part of the lecture, we're going to focus a little bit more on what remote sensing is, while giving an overview of some of the platforms that make up this whole discipline of remote sensing, as well as some examples of applications of remote sensing from different parts of the subdiscipline. So let's start out by approaching this term remote sensing. What is it and what does it mean? So all types of scientists rely on data to make observations and measurements about the world. The data they collect can be used to support or reject hypotheses of all different types. There are thousands of different tools for collecting all these different types of data, but there's one big dichotomy between different types of data collection, and that's data that's collected at the source through direct measurement and data collected from some distance away from the actual phenomenon that's being measured or observed. The first type of data collection of these two is called in situ data collection. That means like data collected at the source. And the second type is data collected via remote sensing. That's that data collected away from the source. There are a few definitions of the term remote sensing. One of them is here. This is a pretty broad definition. It's the science and art of obtaining information about an object, area, or phenomenon without being in direct contact with the feature under investigation. Clearly, that's a really broad definition, and that actually includes things from outside of the geographic world. This broad definition could be applied to all sorts of different data collection types. So here's an example of in situ versus remote sensing data that isn't really in the world of geographic remote sensing or Earth observation. So something like taking a person's temperature, you can do that in situ. If you're not feeling well, you might grab a thermometer, either one that measures your temperature through the ear or the kind that you put in your mouth. But we have remote sensing methods for this as well. You can use thermal imaging to estimate temperature from afar. That's what you see at right. There's a sensor that's detecting the temperature of this person. It can actually tell from a distance if they have a temperature or a fever or not. Here's an example that's more representative of remote sensing within geography or Earth observation. So this is an example from the ecological sciences. At left, a scientist is taking measurements that allow them to measure what's called the leaf area index, which is how much leaf coverage there is in a location. So he's using an instrument here on the ground to measure how much sunlight passes through the leaves of the plant and hit the ground. That's doing this in situ. He's actually measuring it on the ground to get these numbers. But you can also get this data from a satellite at a slightly different scale at right here. You can compute leaf area index from a satellite via remote sensing techniques. So while that term fits that wide range of different types of scientific data collection, the term is usually used to refer to the collection of data related to Earth's surface and atmosphere. It's usually used to collect what's called geospatial data. So geospatial data is data that either has an explicit or implicit connection to locations on an Earth's surface. We'll talk more broadly about geospatial data next time. The example with the thermometer from 2 slides ago, that isn't geospatial data collection. The warm and cold areas aren't tied to coordinates or a location. It's just a measurement that's being taken remotely. When we're using it to refer to geospatial applications, that means all these measurements that are taken have some sort of connection to place or space within them. So here we get a much more strict, kind of zoomed in definition of remote sensing as applied to geospatial data. And there's going to be a lot of terms in here that may not land right now, but this is actually a definition that's closer to what we're covering in this class. You're just not expected to fully understand it yet, so don't worry too much about it. So in this case, remote sensing is defined as the non-contact recording of information from the ultraviolet, visible, infrared, and microwave regions of the electromagnetic spectrum by means of instruments such as cameras, scanners, lasers, linear arrays, and/or area arrays located on platforms such as aircraft or spacecraft, and the analysis of acquired information by means of visual and digital image processing. So it's a terrible definition, but this is kind of an all-encompassing definition of what we talk about when we mean remote sensing in the geospatial world. So obviously, I'm not going to define all those terms today or even kind of uncover what they're referring to, because some of those words require a whole lecture to kind of clarify and show how they apply to remote sensing. but it does get us to a few basic terms that are important to start out with. First, that definition hinted at both platforms and sensors, and these are two key items that allow remote sensing to happen. A sensor is an instrument that's able to capture information about the world. In this example, this array of cameras at the bottom left is a sensor. With a Google car and those cameras that take Google Street View pictures, the sensor is that thing that's on the car that takes the pictures. Sensors are usually actually a lot like cameras, though they don't always take pictures in the visible part of the spectrum. They can take pictures in different parts of the electromagnetic spectrum. That's something we'll look at in the near future, so don't worry too much about that now. Then, in contrast to the sensor, the Google camera taking those Street View pictures, you need something to move that camera around, and that's the platform. The platform is the thing upon which the sensor is mounted. In this case, it's a Subaru. So the Google Street View car is made up of a platform, which is the Subaru, and a sensor, which is that crazy Google camera with something like 11 lenses. For a true remote sensing example, this is a drawing of one of the Landsat satellites that collects data on Earth's surface. In this case, the platform is the Landsat 8 satellite. There's been 8 different Landsats, each one of them is a satellite, and it's a platform for these different sensors that take images of the Earth. On Landsat 8, there's 2 different sensors on board that are able to collect different types of data. One of these is called the Operational Land Imager. This is similar to a big advanced camera. Again, we'll talk more about the specifics of that later. And then there's also a thermal infrared sensor, which is kind of distinct, but takes images in a different part of the spectrum. So more details about how these differ and how they work to collect data will be given in a couple weeks. So we'll talk more about sensor types in the future because it requires a little bit more of a background. It's important early on to discuss the different platforms that are usually considered as remote sensing. So that Google car example, it's geospatial because it takes those pictures and those pictures are tied to a place on the ground. But under that definition we looked at a couple slides ago, it wouldn't actually be considered remote sensing because it's closer to the actual data that's being collected, those pictures. In terms of collecting data about the Earth and really conducting geospatial remote sensing, taking a photo from a few dozen meters away doesn't fit in our definition of remote. Usually we take images from further away to classify these as remotely sensed data. So in the next few slides, I'm going to look at the major platforms that have considered to have been remote sensing. Among the very first platforms for remote sensing were actually pigeons with cameras. They're successful in getting some of the very first images from the sky. So if you look at that picture of the chateau at the right over there, you can actually see little bits of wing as that pigeon's kind of flying around, letting pictures be taken as it flies around. The pigeon is the platform here. That little camera strapped to the pigeon is the sensor. Obviously, this isn't super useful because they're pretty hard to control, but I bet for the owner of the chateau at the time it was pretty cool to just see a picture of that chateau from the sky because that was pretty unusual back then. Other early platforms included things like kites and balloons, as shown here. These were really good at taking surveillance photos or just aerial photos from the front line during battles, for instance. But of course, since these really early platforms, things have gotten much more sophisticated and the ability of these sensors has vastly improved. So among the first platforms were actually airplanes, and airplanes continue to be really important. First, they're really useful for reconnaissance by taking photographs from the air, but later methods developed for collecting more systematic data of large areas from flying multiple flights over a region. Photogrammetry is this related discipline that developed that includes the creation and application of techniques that allow one to actually measure areas on the ground from multiple photographs. Individual photographs from an airplane don't come geo-referenced. They don't have details on where things are. They don't have latitude and longitude, for instance. And they're also often taken at an angle. By using techniques within photogrammetry, aerial photography developed into something that allows you to accurately depict geography and make maps of these different photos. These techniques form the basis for aerial surveying over really large distances. So here are a couple examples of using aerial photography and photogrammetry to actually get some useful data about the Earth. Most of the really high quality data you see on something like Google Maps, when you zoom in really close to a city and you see that basically see an image of the city, those are actually stitched together aerial photographs that have been georeferenced via these photogrammetry techniques. Likewise, photogrammetry made it possible to assess elevation over large areas. Previously, there were kind of surveys that had to take place over vast distances on the ground. By comparing multiple different photographs and conducting these measurements using photogrammetry, we are able to create these USGS topographic maps, basically covering the entire US with accurate elevation data. Then, much later than aircraft-based remote sensing, we have space shuttle-based remote sensing. It has some of the advantages of airborne remote sensing and some advantages of satellites, but also some of the drawbacks of each. So that's a model at right of a space shuttle collecting elevation data on Earth. And that's one of the really useful reasons to collect data via a space shuttle, is you can get, again, multiple measurements, multiple images of the same location, and use these methods of photogrammetry to calculate what the elevation is within all areas of that photograph. So a really common advanced use of the space shuttle based remote sensing, where you're able to measure really accurately the elevation in a location, is called synthetic aperture radar interferometry. So again, big words, don't worry too much about that right now. But do take a second to look at the image at right. This is a technique that allows millimeter scale measurement of deformation of landscapes. So you can see really small changes in the elevation of a location. They're not super straightforward to interpret, so don't worry too much about that right now either. But basically, in the middle of that top map, that area where there's bands of several colors radiating outwards shows that there's been swelling in this area around a volcano in Oregon, where they're close together. Then, of course, there's satellite remote sensing. There's been hundreds of satellites launched all over the world with a wide range of different capabilities. They differ in their orbit types, they differ in the sensors aboard. They can collect really, really regular data over long time periods. So they're really good for scientific applications when you want relatively high quality data over moderate spatial scales, but you want that data continually collected systematically over time. We'll learn more about different satellite remote sensing types in the first unit of this class. But just for a couple quick examples, there's two major types of orbits that allow for different types of imagery to be taken of Earth. The first of these is called Geosynchronous Orbit. This is usually what you get with weather satellites. They stay fixed in one location, and they can pretty much just take images continuously of the same location. This is really useful for looking at large scale changes in the atmosphere, in weather, or looking at the fires we have now. So geosynchronous orbit basically means that the satellite keeps imaging of the exact same spot on Earth's surface. So that means it's revolving around the Earth at about the same rate that the Earth is rotating. And what we have here on the right are a couple examples of this type of imaging. First, this is Superstorm Sandy before it got to New York. Geosynchronous satellites are really good for tracking hurricanes and big weather events like that. At the bottom right, this is from just about a week ago, August 2020, where we have some of the fires in Northern California just starting out, basically. And though it's not super high quality data, you do get an impression of where these fires are and can track them to some degree over time, over a couple days. Then we also have satellites that have a polar orbit. That means that they're swinging around Earth at different rates, but they kind of cross over at the poles as they're orbiting around the Earth. And this allows them, as they're basically doing that orbit, they're taking closer in pictures as they go from pole to pole, and then back down from pole to pole on the other side of the globe. While they're doing that, of course, the Earth is rotating. So over time, these satellites are able to get higher quality images of different parts of the Earth, but they do so a little less frequently than those geostationary orbits. These satellites constantly orbiting around the Earth allow us to get relatively high quality data for comparing change over time. This, once again, is the fires this year, August 2020. These were taken on board the Terra satellite. It revolves around the Earth frequently enough to get a daily image of an area like California, allowing daily tracking of these fires at a little bit higher quality than that image on the last slide. Another example of a common remote sensing platform based on a satellite is, again, this Landsat data. So Landsat data, it's a little bit higher quality than we saw in that last image of the fires, but you have a little bit of a trade-off because it takes longer for the Landsat satellite to get back over that same location. So here we see a substantial change over time. So I think this one is in Palm Springs or somewhere near the Palm Springs area, where you can see a huge increase in the amount of urban development in that region over time. So a huge, rapidly developing area within remote sensing, of course, is the development of unmanned aerial systems or unmanned aerial vehicles, also known as drones. So just to clarify the terminology a little bit, a UAV, that V stands for vehicle, that's usually just referring to the vehicle itself. But in reality, there's always other components involved, including the control mechanisms, the ground reference units, and the term UAS includes these other components that make up the system. Even the pilot is included in an unmanned aerial system. Then drone is usually used more colloquially. I'll probably use it interchangeably with the other terms, and I don't mind if you do either, so no big deal, but usually I'd say UAS or drone, sometimes also referred to as UAV. While all sorts of application areas for drones have been developed in the last 10 or 20 years, in the remote sensing context, we usually focus on drone applications that allow us to gather data about a phenomenon. So this is kind of getting beyond just taking pretty aerial photos or using a drone for like live images of a live event. What we're going to do in this class is look at the different ways you can actually collect durable data that's useful for many different applications using the drone as a remote sensing platform, beyond just as a visualization tool. So there's tons of applications for drone data, and the list keeps growing. One of these is precision agriculture. This image shows a picture in the visible part of the spectrum at left of a field. It all looks pretty green to me, but a drone, by taking images in different parts of the electromagnetic spectrum, including the infrared part of the spectrum, allows us to see indications of plant health that are much better than what the human eye can see. This can allow the targeting of nutrients and pesticides to areas that aren't doing so well. Farmers can look at their field, but it would take a really long time to get this quality of understanding of all these different areas within this field by kind of walking around in them. And also by detecting in different parts of the spectrum, we actually see things that you can't see with just the naked eye. Then of course there's also drone surveying. This is useful for all sorts of urban planning and construction applications. You can use it for construction site planning, upkeep of infrastructure like these power lines on the left or oil pipelines, and you can also use it for updating property boundaries for cities. By processing drone data in remote sensing software, you can get a number of different accurate visualizations in an area, including these orthomosaics, which are similar to the aerial photography images that we talked about before. You can make 3D maps like these buildings that kind of pop out and are really cool for urban planning purposes, or you can come up with like an actual 3D model via LiDAR, which again, we'll talk more about that in a little bit. Those are the main platforms, especially those pigeons, that fit within this broad umbrella of remote sensing as considered in the geospatial world and in geography. An important takeaway from these first few slides is that all these methods are sometimes useful and sometimes not useful. They all have advantages and disadvantages. For whatever reason you're using remote sensing data, there's a number of factors to consider before choosing your platform and sensor and data source. And it's somewhat important to consider that just because something is newer or flashier doesn't mean it's the right tool all the time. So some of these trade-offs are listed on the slide here. I'll introduce some more technical terms for some of these attributes later on, but the trade-offs basically include the following. Quality. I've said the word quality a lot. There's other more technical terms we'll learn for quality. Clearly a drone flying 10 meters or 20 meters away from something can get more detailed information about that small area than a satellite. But the total amount or area that can be collected could also be important. An airplane or a satellite can certainly beat a drone in terms of how much data is collected in a day. Revisit interval is also pretty important. Some satellites, like those geostationary or geosynchronous satellites, can take continuous pictures of the Earth in a given spot, whereas a drone mission may require substantial setup and involvement each time you want to record data. Then there's the length of the data records. Some satellites have been flying around for 10, 20, systems of satellites have been around for 40 years. They might not have the highest quality data, but you can look at changes over those 40 years, which is pretty important. And then, of course, there's cost. This is often a limiting factor, especially for student projects. If you have these grand ideas of what you would love to do with a whole bunch of high-quality drone data, that actually costs a lot of money to collect a lot of the time. If you're doing a construction project with a pretty big budget, you would probably be willing to pay for some really high-quality drone data. But for a lot of research or class project or environmental applications, the free government-produced satellite data works just fine. So that takes us to like a brief overview of the remote sensing process. Beyond just being made up of platforms and sensors, there's a number of different steps that go into actually doing remote sensing work. In this class, we'll focus specifically on a few areas of this workflow. But beyond just getting the data via these platforms, we have to consider a few other things. First, there's the basic physics related to the energy from the sun that drives our ability to capture this data at all. Then we'll go in more depth into those different systems, the platforms and sensors that enable that data collection at all. Different sensors create very different raw products. Different platforms cover different areas at different time intervals, and also they use different parts of the electromagnetic spectrum. Then really a lot of what this class covers is in sections G and H here. Once we have the raw data collected by these platforms and sensors, how can we process it and analyze it to give us worthwhile information that can answer questions? Finally, there's circulation to users. That's a little less relevant in a class like this, but certainly important when on the job, kind of polishing the analysis or images that you've made and making them ready to send out into the world. Before we finish kind of the content section of this first lecture, there's one final important definition to go over, and that's Geographic Information Systems, or GIS. I just want to throw out a little bit of a clarification as to how remote sensing and GIS relate to one another. So first, what is GIS? GIS is often defined using a whole bunch of different words that describe its capabilities. One of these definitions, you might come across similar definitions in your GIS or remote sensing career, but one of these is that it's a computer-based system designed to capture, store, manipulate, analyze, manage, and present all types of geospatial data. It's a really powerful tool for integrating data, analyzing data, and finding new insights. Some of that data that might be integrated with other data or analyzed within a GIS could be, but is not always, remote sensing data. Remote sensing data is geospatial data that can be input in a GIS in any of these ways. So with remote sensing, you can store it in a GIS, you can manage it in a GIS, and you can present it using GIS. But a GIS can also obviously work on other types of data besides remote sensing data, like data produced by the city or the government or just by a person at their computer. So likewise, on the other side, remote sensing work can be done without the use of GIS at all. There are different types of software that don't fit this criteria of being a GIS that can analyze and process remote sensing data. So there's overlap, but the fields are far from synonymous. Because we're using GIS software in this class to do remote sensing work, that ArcGIS Pro software, next week we're going to focus on those basics of GIS, just to kind of like give us a baseline understanding of how to use GIS software and what the capabilities are before we mostly use that software to analyze these different types of remote sensing data.